We've got a man trying to create leverage with a long piece of metal. His force, I'm going to guess, is going straight down. The force of the box on that long piece of metal would also be going straight down based on the force of gravity. I've extended the long piece of metal because that is the line of action. We're going to call the force by the man the applied force, or FA, and then the force from the box, FG, because it's coming from their force of gravity. The angles that they're creating, since those two lines are parallel, are going to be the same theta. So eventually we're going to be able to cancel those two out. We're going to say the torque by the man has to exceed the torque by the box. If it's the same, there's not going to be any acceleration. There won't be any change to the velocity of zero. The question is asking us what torque is required in order for him to move the box, so he has to exceed it by some minimal amount. The force applied by the man times the radius of the man from pivot point times the sine of theta has to be greater than the force of gravity of the box times the radius of the box times the sine of theta from the force of gravity. On both sides, they're going to cancel out those sines of theta. So the force applied by the man times the radius of the man has to be greater than force of gravity times the radius of the box. Just going to divide radius of the man to the other side. The force of the man has to be greater than Fg times the radius of Fg divided by the radius of where the force applied from the man is coming from. It's like setting them equal, but just saying the man has to be larger so that you get that acceleration. Now they're going to give us some numbers. The box is located 0.3 meters away from the rotational center and has a mass of 20 kilograms. What is the minimum force the man needs to apply if he's pushing at 0.2 meters? If he's pushing at a point that is 2 meters from rotation. So we're just going to use our formula. We're going to say force applied by the man is the 20 times 10, which gives us the force of gravity, times 0.3, which is the distance, all divided by the radius that the man is away, which looks like it's 2. So 20 times 10 is 200, times 0.3 divided by 2 is going to give us our solution. Looks like it's going to be about 30 newtons. So as long as the man pushes with greater than 30 newtons, the box will lift upwards. There will be a angular acceleration. So now we've got 3 different places that can be pushed along this axis, and we're trying to determine which force will generate the most torque. Well, that axis that they're pushing on, the force and the axis are all at 90 degrees, so we don't have to worry about the sine of theta because it'd be sine of 90. 90 newtons is x meters away. 30 newtons is 2x meters away. 60 newtons is 3x newtons away. 3x meters away, or 3x distance away. So I'm just going to multiply these. The force times the displacement and see which one gets us the larger number. So 90 times that 1x would be 90x. 30 times 2 would be the 60x. And then the 60 times 3 would be 180x, because we don't know how far it really is. Well, that 180 times x is going to be the largest torque. And it's the largest torque because it gives us the greatest value when we take our force times displacement. Simple explanation here, nothing complicated. So a man is fascinated by physics, is spinning on a rolly chair. The man wants to find his average velocity. Which velocity, angular or tangential, would be the easiest to find? Explain. I'd say angular's easier to find because angular is just talking about how far is he rotating in a certain amount of time. And so if you can just kind of calculate that, it's a lot easier. When we're looking at tangential, with tangential speeds, we would need to incorporate the radius. And honestly, we don't know what the radius is. Where is his center of mass? And how far is his center of mass from the pivot point? Without that information, things become a lot more complicated. So going back to what we initially said, angular is just easier. And this is just going to explain what the man could do. The key that I was looking at that was provided just said angular velocity would be easier to calculate because you can count how many times the man goes around in a full circle in 10 seconds. Divide by 10 so you'd know per second and convert it to radians. We know revolutions are 2 pi radians. I sort of borrowed that answer when I was doing mine. All right, the man owns a very expensive office chair. When his friend gives him a push, he can keep spinning for 40 seconds. However, he does eventually come to a halt, which means a stop, right? He wonders, is there a torque acting upon me that is causing me to stop? Absolutely. In order for the chair to speed up or slow down, for it to experience a change in angular velocity, also known as an angular acceleration, there has to be an unbalance of torques. If there is no unbalance of torques, if he's balanced torques, then he's just going to spin forever. So in order to see that change, that slowdown, there has to be an imbalance of torques. All right, number 4. So we've got like a little dog or horse or something out on the ledge, and we've got a man that's kind of to the left, and it wants us to star where the pivot point is. So that's the last point of contact if it were start to pitch over. Where's the axis of rotation? The situation start done. In each platform, each platform is unit m meters, so you can just kind of count them over and have m meters. What is the torque generated by the miniature horse? So the miniature horse has a mass of 115 kilograms multiplied by 10. That's his force of gravity. And then it is 2 m meters over. So times 2, we know it's going to be in m meters. Then when we multiply that, 1,150 times 2 give us 2,300 m, because the m is still there. It's an unresolved portion of how large each platform is. How close can this man get to the miniature horse before the whole platform starts tipping? So I like this, but I don't like this. So let's just say that the miniature horse is giving it a clockwise rotation, a clockwise torque. So since it's clockwise, that's going to be a negative torque. So we're going to take our torque from the previous problem and call it negative. So negative 2,300 m for the torque. So we want to know when the man gives a positive 2,300 m for the torque, and just say any closer than that, it's going to tip, because it goes from being balanced to being imbalanced in favor of the horse's side. So let's just solve for when will the man be at a positive 2,300 m. Well, the man's force is going to be based on his mass times 10 because of the acceleration of gravity. That gets us force of gravity. 175 times 10. 1,750 newtons of force the man is applying. At what position will 1,750 newtons, what position multiplied that gets us to a balance of 2,300? So we're going to say 2,300 is equal to 175 times 10 times r. We're going to solve for r. And the reason that I don't love this, so we're able to get a solution, 1.31 m, but I don't love this because it's not including any torques coming from the mass of the platform itself. The platform itself has a torque that is in the man's favor, meaning it's a counterclockwise torque, it's a positive torque, and it's excluding that. So if we just for a moment know that we're excluding that portion of the problem, we can solve for what it's asking. But keep in mind, that's not something that you want to just normally exclude, but we're doing it for the sake of the problem that was designed for us. When would you have to do that? Anytime a normal person makes a problem and it's not a test problem or an AP exam problem. It's a worksheet made by a person that just was trying to get you to work a certain way. Anyway, a windmill is currently at rest. Drone hits it. As the result of the collision, the windmill's angular speed will, well, if you hit it, you're applying a force. Newton's second law is net force equals mass times acceleration. A net force causes an acceleration, so it's going to go from 0 to something. The force between the two is shared. So if it hits it softly, it'll hit it back softly, Newton's third law. If the drone had to run part closer, how is the torque going to be compared? It's going to be less, because torque is force times radius. You reduce the radius, you reduce the torque. The greater windmill moment of inertia, the less it will accelerate due to the collision, because I resists change. And if you increase I, you're going to have less change. All right, now we've got an image to the right showing a moment of inertia demonstrator device. Looks kind of cool. Student says moving the weights away from the center of mass does not change the moment of inertia. since the total diameter of the device does not change. Do you agree with this statement? Explain. It's tempting. We can say, well, I equals mr squared, and m is the same, and the total r is the same, but we're not going to agree because it's not about the radius so much as the distribution of the mass. Moment of inertia, I, is calculated, or is it's based on total mass, which didn't change, but also the distribution of the mass. And the fact that the mass is spreading out further from the pivot point, you're going to get an increase in the moment of inertia. You're going to get an increase in sluggishness. You're going to get a resistance to acceleration the further that mass goes out. Calculate how long each of these carnival rides takes to do one full revolution. One full revolution is 2 pi. Well, if it's doing a quarter pi radians per second, how long is it going to take to do 2 pi? Right, 8 seconds. So if it's at a speed of 2 radians, what are we missing? We're missing a pi, which would be 3.14 seconds. If the angular speed is 2 pi radians, well, that's what one revolution is, so that would be 1 second. If the angular speed is 8 radians per second, it would be 0.785 seconds. Again, we're just trying to convert it to 2 pi, how far off of that is. And if it's doing 8 pi radians, it's going to be a quarter of a second. All right, 2 students are about to do some wild high fives. Kind of crazy. If someone approached me like this, I'd be backing off, but okay. The initial angular velocity is 0 radians per second. The acceleration looks like it's 14 radians per second square. And then the angular displacement is 1.33 pi radians. So it looks like they've given us 3 kinematic variables. So we might tend to start thinking this is a kinematic equation. Let's see how it goes. How long does it take for this wind up to take, or how long does the wind up for this high five take? Well, that's asking about time. Okay, well, that's kinematics. Well, we know that angular displacement is equal to initial angular velocity times time. So, plus 1/2 at squared, or alpha t squared. Initial angular velocity is 0, so that times time is still 0, so I'm just going to give it a big circle and an arrow out of the equation. And then I'm left with 1.33 pi is equal to 1/2 times 14 times time squared. And I'm going to be solving for time, solving for t. So take my 1.33 times pi, or 1.33 pi in my calculator. I like to hit enter so it registers the number. I'm going to multiply by 2 to move the 1/2 to the other side. Dividing by 1/2, multiplying by 2, same thing. Divide by 14, and then taking the square root so that I solve for t. So I got 0.77 seconds is my time. What is the final angular speed right before the high five impact? So we're wanting to know what the angular velocity is. We're looking for omega. So omega is equal to omega naught plus alpha times time. Omega naught is 0, so we can take that out of our equation. We're left with omega is equal to alpha times time. Alpha we were provided at 14, and time we solved at 0.77. So omega, or final angular velocity, would be equal to 14 times 0.77. And we get 10.78 radians per second. Or we've got two gears that are touching tooth to tooth as they're moving. So they have the same linear velocity or tangential velocity because they're tooth to tooth. They're each moving at the same spigot at the same time, or whatever. Spigot's the wrong word. But what is the angular velocity of the large gear in terms of radius? Well, velocity is omega r, so omega is equal to v over r. And we know that the velocity for both of them is 0.2. The radius is 3r, so if we divide that, we should get some number close to 0.067r. The smaller gear's angular velocity is doubled. How does that affect the angular velocity of the larger gear, or the large gear? Well, so the angular velocity is doubled, so omega is doubled. And then their relationship is directly proportional. So if you double omega, you double velocity, right? Because it's omega velocity is equal to omega r. So doubling one doubles the other. We haven't changed the radius, so we know it's still that direct relationship. If omega is doubled, then the smaller gear's tangential velocity also doubles because of the relationship v equals omega r. The two gears share a tangential velocity, so the bigger gear's tangential velocity also changes. If the big gear's tangential velocity doubles, then its angular velocity also doubles. So I'm just showing that if I multiply by 2 on one side, you got to do by 2 on the other side. A bike wheel is spinning at a constant angular velocity of 4 radians per second. Constant velocity is what's important here. Constant velocity. What does constant velocity mean? The net torque would be 0. What is the average angular acceleration of the bike? It has to be 0 if it's constant velocity. Explain your answers to A and B. Constant velocity means equilibrium. Equilibrium in this case means balanced torques. Balanced torques means there's no angular acceleration. All of these things mean the same thing. When we were in linear, we said that net force 0 means equilibrium, means balanced forces, means no acceleration, means constant velocity. The velocity doesn't have to be 0 for this to be true. Any constant velocity, 0 or non-zero, these things are true. All right, now we're spinning a rolly chair again, 500 newtons of force for 5 seconds. In the experiment where the force is applied, what additional information would be required to calculate the acceleration resulting from the 500 Newton force? Well, this is an angular acceleration because they're spinning them, and we know that torque equals Ia, so torque equals rotational inertia times alpha. If we divide rotational inertia to the other side, we would get alpha is equal to torque over rotational inertia. If torque is force times radius, so our acceleration is force times radius divided by rotational inertia. What do we know? What can we plug in? Well, we know force. We don't know radius. We don't know rotational inertia. Those are two things we would need to know based on the information that we were given, what we know in order to calculate the acceleration, the angular acceleration. In the experiment where the pushing student provided a constant linear velocity, so it looks like they're pushing with enough torque so that it balances any frictional torque. So you've balanced your forces, you've got a constant velocity. What additional information would be required in order to find the angular velocity of the student in the chair? Here, I'm going to take a look at the key that was made by the designer of the worksheet and just see what it says. We would need to know how far from the center of mass the kid who is pushing at 5 meters per second is, so we can use the formula V equals omega r. Okay, let me read that again. We would need to know how far from the center of mass the kid who is pushing at 5 meters per second is, so they're saying, okay, well, where's the force being applied? What's the radius? So that we can use the formula V equals omega r. Again, we're looking for angular velocity. Angular velocity is equal to what we're looking for. We know the linear velocity is 5. If we know what the linear velocity is, what we need to know is what the radius is. Knowing what the radius is, where the force is being applied, or knowing what the radius is will allow us to solve this, because V equals omega r, omega equals V over r. If we know V, we need to know r.